this. And we can find this by assuming f of x to be a simple function such as this one. Under this assumption, right, this assumption 1, we get a to b. Because of this assumption, it is 1. And because of this assumption, this part is 1. Then we have an equality. We can solve this for W1 to get some number. And similarly, we can also assume that the function is simple, but not exactly this one, a little bit different one. Then under this assumption, we can write the equality using x. And then using this relation, f of x1 becomes x1. Because we know W1, this is a number times x1 equals some number, also we can do the calculation, and x1 can be found. This is the way we find it. Any questions about the things that we studied? Then today we will study about the different way of solving a system. Generally, what we did were either exact or iteration. Exact means we are solving a system. Using Gaussian elimination or some kind of decomposition and find the solution, right? Find the solution. And iteration is the idea of guessing the solution in the first place, and by plugging this into the system, we find the next vector representing the solution, and then we do these things over and over again to arrive at the solution. These were covered last time, and today we will cover a different method. It came from geometrical interpretation of the curve, but assume that we sketched n-dimensional curve in 2 dimensions. So it's n-dimensional, somehow image of 2-dimensional representation. Then to go to the top, how can you do it? We generally start at some point, and then we follow the perpendicular direction at each time. At each time, we find the perpendicular direction, and then we may arrive at the solution. So this idea is all analyzed and then formed in the method. So I will grab the part having this formula. So the method called conjugate gradient method comes from this kind of idea, and it is all written in this unlucky, so I will just magnify and copy this portion and copy the other portion later. So this is it. So please browse the idea. The idea is going to the solution, not by just random iteration, but by following a certain path that came from the idea that I explained, to go to the top in 2-dimensional case, right? So this is the 2-dimensional image of n-dimensional stuff. So idea is in n-dimension, but it's difficult to sketch n-dimensional things. So we sketch 2-dimensional version. So assume that you want to go to the top. then how? We initially go from this point to the perpendicular point, and each step we follow and find the perpendicular path to arrive at this point. And all these ideas are combined together in the method. So conjugate grade method came from that, and gradient is the gradient direction. Then how can you do it? First of all, you should know what is what. Here, alpha, beta are numbers. So when you see alpha, beta, these are all numbers, right? These are all numbers. So you should know what is a number, and all others are vectors. So did I circle all the numbers? Let's check. I circle all the numbers, and all others are numbers. All others are vectors. So all the numbers are circled. Then let's do it. To arrive at the top, we start off with x0 vector, right? This is x0 vector. And we also define r0 vector that happen to be the right-hand side of the equation. We have the equation such as this one, linear system, and this right-hand side becomes r0. And then also p0 vector. So we start off with these vectors. But to use generic subscript, I will remove this subscript, this specific subscript 0, 0, 0. But in initial step, it is I equal to 0 step, right? When I is equal to 0, then this is used. So this is the initial step. And we usually start off with 0 here. And we usually start off with this column vector b, right? And we initially start off with 0, 0. Then the next thing is looping, meaning we are doing many calculations up to this point. So we do the looping from this point to this point over and over, right? So we do this thing and go up, and then go down, go up, go down, and so on. So we do these things over and over again. Then what things should be done? First of all, k is the running variable, right? So k is the running variable. Then k equal to 0 gives us r0 is 0, right? So assume that, so I will let you know what it means. We do this thing. We do, where can we write? I will go back and forth between third column and second column. Second column will keep the vectors and numbers. Third column will keep the information or explanation. So this is the idea. Each time we find something. So what do you want to solve? This is the goal. We want to solve this differential equation, and we don't have the solution. We don't have the solution yet. So each time we plug in something similar to solution, not necessarily the solution, then they are not equal. Do you follow me? Generally, these are not equal. So you should understand the idea. You want to solve ax equals b. We want to find x satisfying it. But generally, for our xi is not equal. So what you do is finding the difference and call this r, right? Call this r. So this is what we do. Call this r vector. Generally, r vector. So assume that this happened to be 0. Assume that this happened to be 0. Then what does this mean? This xi is the solution to the problem, right? So when do we stop? When r vector is a 0 vector, we stop. So when r vector is a 0 vector, we stop. So we know when to stop, right? When the difference between the right-hand side and the left-hand side is 0, right? Between the right-hand side and left-hand side is 0, we stop. then we iterate not infinitely many times, but finitely many times. We iterate these things. But I will describe this one more time. If R happen to be 0 vector, right? R vector is 0 vector, then we stop. Then let's follow. So take a look. We are looping it. We are looping it from this point to this one. If Rk is already 0, where k is 0, so I will write the indicator. I used I, but the method used k, so I will delete the I notation and then replace these things by k. I don't want to confuse you. I use I, text is k, then you are confused though. I will use the same subscript k. Then k is equal to 0 step is written here. Then initially take a look. Is the right hand side, is Rk 0 or not? Generally, when you solve the problem, B is not 0 generally. So this is not 0. Of course, when you have 0 on the right hand side, 0 is a solution, trivial solution we can find. So when the right hand side is 0, we can stop. So when this is 0, we can stop. Right? When this is 0, we can stop. This R means the difference between the right hand side and left side of the equation of the system. So if the difference is 0, we stop. P will be mentioned later. So that is the way we follow the perpendicular direction each time. Then take a look. Initially we said this is 0, artificial, right? And this is given by the problem. Then this, if this is equal to 0, we just stop, right? We stop and the solution is 0, right? But if this is not 0, then we go to the next step. So let's go. Because k is still 0, we don't determine beta. We don't determine beta. So I will write beta column and alpha column. So alpha column, beta column, and beta is not defined, right? Not defined. Because take a look. Here only when k is greater than 1. K is 0, it's not, right? But when k is greater than beta is defined. So it is not defined. Then the next step is this one. As you can see, P, k plus 1, then P sub k plus 1 is what? P of P sub what? 1, right? So P1 will be defined, right? P1 will be defined. P1 equals, as you can see, Rk, right? Plus beta is initially defined here. 0, I didn't write it here. So beta is initially defined here. So it's not defined from this formula, but it is defined here. Beta is 0. So it is essentially P1 is R0 plus 0, right? R0. So this is the one, right? This is it. And then afterwards, take a look. Afterwards, we follow each step. We define alpha 0. We define alpha 0 by doing this multiplication of vectors, right? Multiplication of matrices. So we multiply R transpose row vector and RK column vector. Then it's a number. And then P vector, right? P vector transpose multiplied by A vector multiplied by this, and it happened to be 0 because initially P vector is 0. So this multiplication is done. So we follow these steps, and let me briefly check the condition one more time. Beta is defined, alpha 0, strange, a little bit strange. Right, pk plus 1 is rk, so it's not 0. I was confused. This is k plus 1 subscript, so rk So B transpose A, B, right? B transpose A, B. So the denominator is not 0. I was confused between. So take a look. This one, transpose multiplied by this one, over this one, right? Transpose multiplied by A by this one, right? So this, so let's pick some example. Assume that the right-hand side is, so first of all, let's make up a problem, then it's easier. So we are solving AX equals B, where A is 1, 2, 3, 4, and then X matrix equals B, and then 3, 7, right? We are solving, assume that we are solving this equation. Then, as you can see, what should follow? This I will refill this thing instead of just arbitrary description here. I will really fill these things with this assumption. Then it will be easier to follow. Do you agree with me? So let's do it. Initially, we should have 0, 0, right? And then RK is the right-hand side, 3, 7. PK is 0, 0. And this is it. Then let's determine this P1. P1 is determined by just copying it. So I filled these things, and now I want to fill this blank spot. This blank spot should be filled. So let's do the calculation using MATLAB. So I will do the calculation using MATLAB. And as you can see, this is the step we want to do. We already, take a look, we already calculated P1, right? We already calculated P1. It's time to calculate alpha 0, right? It's time to calculate alpha 0. How? It is RK transpose. I will create this thing. RK is 3, 7 vector. Do you follow me? This is RK vector. So RK transpose multiplied by RK should be done, right? 58. So I should do this thing, right? 58. I did the calculation of this thing. It is 58 over, and then I will do this thing. I will do this thing. So PK is RK, so I can directly use RK. PK is RK, right? And A matrix is 1, 2, 3, 4. So PK transpose multiplied by A multiplied by PK should be done. In fact, K plus 1, right? K plus 1. I should have used K plus, but let's say PK. PK plus 1 here, right? So 310. So if I do the multiplication, it is 310. Beta K? You mean beta K? Yes. Beta K is the initialization. When you initialize, beta is 0. So initial step, these things were assigned. 4 things except alpha were assigned. 4 things except alpha were assigned by the initial step. Only thing missing here is this one. But even before calculating this, we calculate P1 first and then came here. So I will write the order of calculation. So first thing, second thing, third thing, fourth thing, and then fifth thing here. Fifth thing, and then using this thing, sixth thing, right? So we calculate in this order. So we calculate everything in this order. Then alpha is determined, right? Then the next step is K. Still K is 1, so X1 should be calculated, right? We should calculate X1. So X1 should be calculated. And then X1 happened to be this number plus this alpha K plus PK plus 1. So it is 58 over 310. I will write it. 58 over 310 multiplied by pk, right? pk plus 1. Right? This is pk plus. So this is it. So the next calculation is 0.50613, and this is 1.309. Right? So this is the result of the calculation. And if you have 3079. So take a look and then check whether you completely follow up to this point or not. The seventh calculation. I'm just following this. And the next thing is, now using this result, we check whether this is close enough to the solution. In other words, we check the right-hand side and the left side difference, right? We check the difference of the right-hand side and left-hand side, and then check whether this number is small enough. So we now do the next calculation and store the result here, right? This is the eighth calculation. So let's do it. B minus this thing. So I will implement everything. B is 3, 7. I guess I did it, but it doesn't matter. B is this one. And then pk plus 1 should have been used. In any case, this is now set. Then I will do the calculation like this. I will do the calculation like B minus A multiplied by AXK plus 1, right? I will do this calculation. I will call this X. What happened? Yeah, this is called xk plus 1, right? This is xk plus 1. And now I will do this thing. rk equals, ik plus 1 equals. So rk plus 1 equals b minus ak plus 1. This is what I will do. So rk plus 1 equals b minus a times xkp plus 1, right? So I'm just implementing individual steps. Then we get this number. Now take a look. Initially, 3.7 was the difference between the right-hand side and left-hand side. Now look at the difference. Difference is already small. What is the goal? Making this difference equal to 0. This is the goal, right? Right-hand side and left side, the difference is small. So if we do this thing, then I will copy this number. I will just cut it 2 decimal position. Now I have found the difference. It is 0.77. About 8 is equal, right? 7.7 is okay. Let's write 7.7. This is the result that we can get. Oh, 0.77, sorry. 0.77. So in any case, roughly this is it. So do you follow me? So each time we get the minimal, we get the difference, and we somehow shrink this vector. This is the goal. We shrink this vector. Then what is the next step? Next step is looping it, right? So we go to the top and then follow the same step. We should determine beta value. Beta value initially assigned, but it's possible to calculate beta value. So let's do it. Beta value should be calculated. So beta k equals rk transpose multiplied by rk So I will open the formula part instead of that, then it's much way easier, right? I'll just open this part. So what I'm doing is this one, right? RK transpose multiplied by RK over the previous RK. This is what I will do. So RK transpose multiplied by RK and then the previous value. So this is what I will do. So please check these things and let me know whether you completely follow the steps or not. Do you completely follow the steps? Then let's do it. What is wrong? Parentheses. So take a look. Already very small number, right? Beta k is a small number. So it is, so this number is a small number, and then it is 0.0006 something, right? So each step you calculate these things and continue to minimize the difference. And then afterwards, almost the same thing over and over again. Take a look. We already did this kind of things before, right? We just multiply RK and then we make this new vector, right? PK plus 1. So I will do this step with you. So let's do it. Now we will define PK plus 1 using PK plus RK PK plus 1 is RK, and then plus beta k multiplied by beta k multiplied by PK. Right? This is what I did, right? So here, computer recognize the previous value and new value, right? This is the new value, this is the old value, right? So this is what I do. This is what I do. So in the actual program, you should be careful about the index. Then this is PKP, right? PK next. I will copy these values. Negative 17 and 08, 17 and 08. So do you follow me? So please follow the order. We should always calculate this way. I will just indicate the order. First, second, third, fourth, fifth, sixth, right? And then seventh, eighth, ninth, and then 10th, and then here 11th. 11th is the calculation of alpha 1. Right? Alpha 1. So we do these steps, and once we hit the 0 vector here, or some vector very close to 0, we can stop, right? Once we hit the 0 vector, or if it doesn't hit 0 vector, we end the step after how many iterations? Total 0 to n minus 1 iterations, we stop. So it's not infinite, it's not an infinite loop. We should stop. Either way, when this difference is 0, we stop, right? Or when we loop. Usually it is the number n is given by the number of unknowns. So in this case, how many unknowns do we have? 2 unknowns, right? So when we hit k equal to 1, then we go all the way, and then we don't go back because already we hit the last limit, right? And then, so let's continue because we are very close to stopping this routine. Then this is it. And then afterwards, we should calculate the value. We already calculated beta k, right? we calculate this one. So it's time to calculate alpha 1, right? Alpha 1. And then after going down, we cannot go back because 0 and 1 case are done with 2 unknowns. So let's do it. So alpha k is, I will write that part. So it is this. Alpha k equals RKP transpose multiply RKP over PKP transpose multiplied by A multiplied by PKP. This is alpha k. Then it is negative 2.67, right? Then this number should be used upstairs. Any questions? And let's do it. Negative 2.6. I will write the number. I will finish it. And then finally, xk should be calculated, right? So xk plus value should be xk previous plus value times alpha k multiplied with pkp, right? And then rkp equals b minus a multiplied by xkp. So we got some result, but somehow I think our calculation might have some mistake. But in any case, once we hit, we should just stop at this moment. And then we write the xk as the solution. In other words, the final xkp is the solution, right? This is the solution to the problem. So this is. Right, yeah, it's properly, but I don't know where I messed up. But roughly, this is the idea. So when you properly do these things, we arrive at 0, 0 value, but somehow I might use different xm in actual calculation. But in any case, you can do these things to find the result. So take a look. We generate essentially this difference factor, right? So solution guess, right? This is the solution guess factor. This is the difference factor. And all these are auxiliary, right? So these are used to somehow create the new value. So old value creates new value, right? And then this value creates the next value, right? About 1 point something, right? And then 1 point something, right? The new value. So we are trying to find this is the solution, right? This kind of thing is the solution by doing these things. So roughly, I completely showed you all the necessary steps. And please check and let me know whether you can really implement these things. As you can see, in actual implementation, you won't need 20 lines. You won't need 20 lines. One thing that MATLAB cannot handle is the zero-based index, right? MATLAB cannot handle zero-based index. So it's a good idea to rewrite these things using one-based index. So instead of starting off with 0, you can start off with one-based index, right? So k equals 1. So here, 1, 1, 1, 1 can replace it, right? Then instead of 0 to n, 1 to 0 to n minus 1 to n, because we start off with 1. Then r, this is okay. K is greater than 1, right? And all these are the necessary changes. But in any case, the idea is starting off with some position and then follow the perpendicular direction each time to generate better x So this x is the initial x. Then we generate better x following these orthogonal conditions. And then after that, we go to the better vector, and each time we can check the difference, right? We can check the difference between this right-hand side and the left-hand side, right? So this is stored in R vector. And this R vector should shrink, but somehow, in my opinion, my alpha value here could be wrong. My alpha value here or something could be wrong. But in any case, if you make this kind of method, then how many times should you run? At most, the number of unknown times, right? So in this case, how many unknowns? 2 unknowns, right? In this problem, we have 2 unknowns. So this is called the conjugate gradient method. And I will let you browse one more time. And afterwards, I will continue and cover the next thing. Please browse this thing one more time and ask questions.
Why do you pick a value for the number of iterations based on the unknown and based on the difference between whatever beta minus or b minus beta?
We cannot get any better after that iteration. If we go further than that, we may even go worse. We may go down. So we should reach the goal, and we should stop instead of going down.
Well, what I mean is, normally in an iteration, I'll just get some, maximum difference.
That's right. But in this case, we are choosing the gradient direction. And gradient direction is set each time, and then we arrive at the goal at certain amount of time. That's the setting. And then afterwards, if we iterate more times, then it follows the other gradient direction and it may go worse.
What is that greatest value? I guess I don't understand what that concept really is.
It means the solution. In other words, like we want to minimize this thing, so we make it upside down, right? We make it upside down. Then going up means going down, right? So we go to the smallest difference of these things is called the optimal point. But if you want the full explanation, then I will explain it at my office. You can come to my office, then I will explain the reason why we are having these things. But generally, the idea is each time we minimize the norm, right? We minimize the norm of this kind of thing. This is B, right? So this kind of thing. And then we may use infinite norm, 2 norm, or some norm, and then minimize this thing. Then with this condition, we get the coefficients like this. We get the coefficients like this. Right? We get the coefficients like this. So it's a little bit trickier step, but roughly, we always find the orthogonal direction to minimize it. But we don't go too far. In other words, we don't have to iterate more than the number of unknowns times. So if we go more than the unknowns times, then we may begin to go down. Yes? Yeah, that one is only regarding k as k plus 1 or something like that, right? Regarding this k as the one less value, then if you use capital K instead of using, so it is a straightforward conversion of unknown, variable. So we are using k, right? So k should run from 0 to n minus 1. But we are using capital K. So have capital K to be lower k plus 1. Then straightforward conversion says what? K should run from 1 to the straightforward conversion. There are some restrictions. But in this course, we don't want to cover that. As you can see, the very general case is solved in general problems, but the method may fail in some cases. There are some cases. But in this course, we don't limit our application very much. Any other questions? So roughly, the method was created theoretically, but in this course, we don't cover the reason why this method works. But we cover the method itself, and in advanced courses or in like reading courses or maybe private tutoring, you may ask the reason why this is derived. In fact, when I first came here, I covered all the details of proofs. Sometimes I used 3 lecture hours to prove things, but people didn't even know to implement this thing itself. I realized it's more important to really implement and later check why it works or the proof part or the limitation of the application of this thing to one matrix definitely. In any case, this is called the conjugate gradient method. Roughly, in visual sense, we are trying to go to the optimal position or solution, right? Assume that this is a solution position. So we go to the solution position by optimally following past x0, x1, x2, x3, x4, and then xk, that happen to be x capital N, that happen to be the number of unknowns, right? So x1, x2, xn, right? Assume that we have 10 unknowns, then x1, x2, xn, then we arrive at the solution. So roughly this is it, and be careful about the indexing because take a look. If you follow this thing, then with capital K it's from 1 to n. Do you follow me? It's 1 to n. Then what about this thing? What about this thing? This should be what? N plus 1, right? N plus 1 is made where? Right up here. X plus 1 is made right here. And n is used upstairs, and this becomes n plus 1. The total n iterations. Initially x0 is assigned, but each iteration creates new x. We have total n iterations, so we get this. You follow me? So initially we had x. There are total how many x? Total n plus 1x. So 1 is already there. But each time, in each iteration, we get one more. So we arrive at xn plus 1. If you use MATLAB, if you use other languages than MATLAB, where zero-based index is allowed, then you don't have to touch anything. Just use this. But if you use MATLAB, convert lowercase k to uppercase k. So convert everything involving lowercase k because it uses one-based index. So all these things should have different index. So conjugate gradient method is used in some areas, and it's good to know about at least the algorithm at this moment. But if you really use these things heavily, then it's good to study about the derivation, meaning the proof, right? And the limitation. For what A can you use it? But in this course, we don't. We just apply these things on nicely working matrix. But later, when you major in or use these things heavily, then you can do those. But here, we don't even go there. So roughly, this is it. So we are adjusting x each time by following orthogonal direction, perpendicular direction. That's the reason why we get these kind of strange things. Just norm calculation and then doing stuff, do this kind of solving for some number, and then that kind of adjustment is made on this x vector, right? Adjustment. So x vector plus adjustment, right? So we initially get the solution, and then the solution is not good enough, then we adjust about this amount, right? And then we check. And then we readjust, and then check. We readjust and then check. Somehow my example had bad alpha k. I don't know why, but at least if we get correct k, then we will get better result. So look at this and check, and then we will continue. So roughly, P, alpha, beta are all auxiliary. These do not do the major role in our investigation. Our investigation focuses on X, right? And then difference, right? So we focus on these two things, X and R. X is the solution part. R is the difference between the solution and the right-hand side, right? So we focus on these two things, and all others are auxiliary. So roughly, you grab the idea. Oh, just bookkeeping work here. Up to this point is bookkeeping. And roughly, auxiliary terms are calculated here. And then adjustment is made, right? We adjust this value a little bit to create new value. And then check the difference. And we readjust. So in short, this algorithm, I will mark the important part. So roughly, this is the situation. We have all these things, but you should focus on this part. This is the major part, right? Other things are, in some sense, auxiliary. In other words, somehow you can define differently, but you may get the same result, right? So this is the key part. These two things are the key part. So these two things, right? Others are all adjusting this value a little bit, and then making the X and X better, and shrinking this difference, right? Making this better, and then shrinking the difference. Yes. When it is created, it is to this side. So when you start off from 0 position, and of course we have bigger size vector the same. We always start off from 0 position, and then follow certain paths to arrive at the goal. Yes? Initial xk is always 0. Initial x is 0. So x0 is always 0. Or initial difference is always the right-hand side. Because a times 0 vector is 0, subtract, right? So b minus, so always right-hand side is the initial. So initially, these are the starting point, and then we now change these things, and this will become 0. This will become solution. So in my opinion, it's not very difficult to program these things, but let's check the implementation side. As you can see, do we need both previous result and new result? When? When do we need both previous and new result? Here and here, right? And here and here. Other than these two positions, we don't need both previous and new result. For instance, do we need x1 and x2 together at some time, or xk and xk plus 1 together? Do we need that or not? Check it. Take a look. Let's follow x. X is here, right? And where? X is here, right? Then assume that x is changed. In other words, we just keep one memory position to keep x. Then what happens? After this step, if we keep just one memory position for x, this value will disappear. But will it matter? Afterwards, will it matter? Take a look. We don't need the previous. So in this sense, as you can see, x needs just one placeholder, right? One memory space. What about r? R requires two different. So for r, you may keep r previous and current r, or r k minus 1 and r k. What about p? What about p? P k plus 1, and then pk are both required, right? So pk plus 1 pk, so both are required. So p needs 2. What about alpha and beta? First of all, beta. Beta is set here, and new beta will be set here, and then after new beta is set, will we use beta k minus 1 or not? We don't need beta other than this position. So beta requires just one memory position. Finally, alpha. Alpha is set here, then used here, done. So in this sense, you can program it, this thing with, I will write it. You can program it with x, right? R previous, current R, right? And then P, and then next P, right? P next. Because, as you can see in the formula, we determine P, and then P is used to determine pk plus 1, and pk plus 1 is needed here. But, oh, I was confused. Yeah, once this is determined, even P is not necessary. Sorry, I was confused. I only thought this part, and I thought this plus is for the whole thing, not the subscript. But thank you. Even P requires just one memory space. Only R requires, I was confused between this. I thought it was pk, but it was p sub k plus 1 attached together. Sorry for that. This is subscript. So once we set new pk plus 1 after this, always new k plus 1 is used. So we don't need two memory space. Then finally, alpha and beta. Alpha, beta. So roughly, you program this thing using these things, right? You program this thing using these. The only tricky part is R previous and R. So once you set new R, do not forget to set this by keeping old R. Do you follow me? So once you create new R, then set this thing by using previous R. You should be very careful in this program. If you are not careful, in other words, you directly set new R, then old R is gone. Do you know what I mean? If you are not careful enough, so say like this. Oh, R equals, this is new R, right? New R equals R plus P, something like this is used. Then what happens? This R became new R, then old R previous, right? So R previous is confusing because we use P2, so I will say just old, right? So will this work or not? Will this work or not? What happens? Using previous R, we determine new R, right? But can you track down the old R after this? This R is gone, right? So before this, you should write this. Do you know what I mean? So this is the trick. So you keep R in R old, and then use R to determine new R. So this artificial part should be added, even though it's not written anywhere. So take a look. When you see the algorithm, it has a lot of subscripts to describe the situation. But in real program, you can remove a lot of subscripts like this. You can remove a lot of subscripts like this. Only possible subscript might be this place, right? No. This place, right? Then even in this place, you don't need subscript. You just say R older than just R, right? R older than R. And then about the time you determine R, right, this place, right before this place, you add right before this place, you add R old equals new current R, right? And then you completely abolish subscript in the actual program. So please browse the ideas and ask questions. So I will return back to the bigger version. So only at this position, right? Only at this position, before this position, you set old R equals current R. And the current R, yes. Then the program is very easy, right? Very easy. X equals 0, 0, 0, 0 vector, right? R is 0, 0, 0. R is B vector, like 3, 7. And then P is 0, 0, 0 vector, column vector, right? And then beta is 0, right? You don't need any subscript. And then when K is equal to 1, you are looping from K1 through N. Or I will just follow this thing. Not like case, you should convert this number to capital. Okay, so K is equal to 0 through N minus 1. Because K is, because here we say R is equal to, check whether R vector is a 0 vector or not, right? R vector is not 0 in the first place. So we just skip this third step. And in the first step, K is 0, so we just skip this thing. And we come to this. P equals R, current R, right? Current R plus B times P. And we need previous R and this one, right? Previous R is B, right? R old is B. And then R new is not even set here, right? R new is not even set. So this part is tricky here. This part is tricky because R is 0 vector. And in this step, we should be careful. Because, do you understand the situation? It is P1 that is determined by R0 and beta. Oh, no problem. R0 is used to then. In the first step, R old is not even set. R old is, at this stage, R old is not even set. R.
Isn't it beta or B? I mean, R old. Don't you start out with R old with B?
B is not beta. B is the right hand side.
Right. We were talking about initially setting R old, right?
R old will be set here. R old will be set. Just before this, R old will be set. So in the first step, R old is not even used or set. R old is not set in the first step. First pass. In the first pass, R old is not even used or set.
Okay, I'm confused with what you mean with R old and R. Once you get inside the loop there.
Yeah. But when K is equal to 0, we don't have R sub minus 1. We don't have R old. When K is equal to 0. So just R is used here. Current R is used here. And R old is not even necessary. So what I mean is the implementation of this thing. So I will write down the implementation one more time. Then it will be clearer. So let's go down and then recopy this thing. So I will copy these things. So I will write down the code on the right hand side, right? So you code this way. X equals a 0 vector of given size, right? So it should be a column vector, right? Do you follow me? it should be a column vector. So X is defined, right? And then similarly, R should be defined by using the right-hand side, such as 3, 7, column vector, and column vector, right? Right-hand side of the equation. And P is a column vector, 0, 0, 0 vector, right? And then beta, I used B to represent beta because B is given by the problem, so I just use this thing. Beta is 0. So this is the first step implementation. Now the second step implementation for certain index k running from 0 to n minus 1, right? N minus 1. And then we are looping it. If k is 0, then first of all, I didn't do the third line, so I will do the third line first and then do this line. The third line is this one. If R, k is not necessary, right? R is a 0 vector. It's not a real code. You should really implement these things using your language and syntax, right? I'm just giving you the idea. If this happens, then X equals, X is solution, so I will just say solution. Solution equals X and stop, right? And then stop. And if, right? And if. So this is the first stopping condition. In other words, if the difference is 0, then we stop. Do you follow me? So I implemented up to third line, right? This is the third line. Then fourth line, if k is 0, if k is equal to 0, then continue. Continue is not a good idea, right? So if we just continue might be okay, right? So if we hit 0, then we don't have to, oh, sorry. Yeah, it's not correct, sorry. We should implement the same way. This is incorrect. So we should say if k is greater than 0, right? If k is greater than 0, then v beta k equals R transpose multiplied by R over R old transpose multiplied by R old. Right? This is the one that you write. And if. So I wrote down up to fourth line, and if you have a question, ask me. Maybe this side or so because our old itself is not even defined, right? Our old itself is not even defined, but as you can see, because if k is greater than, less than 0, k is equal to 0, it doesn't even come into this place, right? But it's a good idea to have this kind of thing defined, because if we don't define it, it may complain, right? So R old could be just R. It's not even used, right? This itself is not even used. But I defined it because the computer may say it's an error because RO is not even defined. Do you know what I mean? RO is not even defined and it's used in the syntax, right? In the sentence, so you may complain. So because of this reason, I added this thing even if it's not necessary in the theory. Do you follow everything up to this point? In other words, as you can see, did I use any subscript here? Do you see any RK, PK? Do you see anything like this? So in actual programming, you can remove all the unnecessary subscripts or superscripts. Only for human interpretation, we attach to these things, right? Only for human interpretation. So up to this point is implemented. Then fifth line, very straightforward. Fifth line is very straightforward. Pk plus 1 equals Rk plus beta times, right? Beta times Pk. Done. Very straightforward. Then I will use my note instead of going back. And the sixth line is alpha k, right? Alpha equals Rk transpose multiplied by Rk over Pk transpose multiplied by A matrix multiplied by Pk plus matrix. And then x is equal to previous x plus A alpha and then Pk. And then Rk, now it's time to use R ORed, right? R ORed and then now R, right? Do you know what I mean? Because both R and R ORed are necessary in the formula. Now I use R ORed. And then now we really determine R. R equals B minus A multiplied by X. And then seventh line is end of loop, right? End of loop. Right? End of loop. Yes? It didn't matter. I saw it didn't matter. It's possible to use parentheses, but it didn't matter. Yeah. Somehow, when I wrote down the division and then multiplication, it mattered, but it didn't matter. Right. Yeah, it didn't matter. But only when we removed this parenthesis, it mattered. Then eighth line is what? Solution equals the x that we found, right? This is it. So take a look. By doing this, you create the complete algorithm that will work. So as you can see, once you see the theory, you should know how to implement. And as you saw, in this case, index is not necessary in your actual program, right? You can remove your index by using this kind of relation. This kind of relation. In human mind, x is not equal to x plus 1 in human mind, but in computer program it's possible. So this is previous and this is current. So by doing this, you can have a running program. And please check this kind of idea and use this kind of idea when you implement in the future. So once you see many subscripts or stuff like that, you should correctly interpret and then create this kind. If you create this way, your program will use less memory, right? And it will run very fast. If you don't create the program this way, in other words, you keep all the subscripts in array, then when the size of the matrix grows, it may be very slow. It may become very slow. But if you use this kind of thing, it is almost a linear level. It's like an O(n) level. So if you have a size n matrix, then you just use n times this amount. So I will show you both the theory and the algorithm that you can use. And then please check whether you can really understand these things and implement. And our only thing remaining might be the theory part, deriving these formula, especially these auxiliary things. How can you derive these auxiliary things? Is the only remaining. Then the next thing is handling nonlinear system. We have handled linear systems, but what if we need to handle nonlinear system? So assume that you are solving this kind of system. It's not linear anymore. In other words, all the theories or methods that we learned are useless here. Then how can you handle this kind of problem? First of all, in this method, we convert the problem into different pattern, different form. So we convert the problem into this form. Why? We want to name these things using these f sub something, right? So first function is f1, right? And f1 happens to be 0. Second function is f2, f2 happens to be 0. Third function is f3 happens to be. Do you know what I mean? So when you want to use Newton's method, you should convert the problem into this pattern, having 0 on the right-hand side. When you use iteration, you should have x equals something pattern, right? When you use iteration, x equals something. But when you use Newton's method, you should have this pattern. In other words, f1 is not x1 squared plus x plus x3. It should be those things minus 1, right? Minus 1 should use it. So this is the part you should be careful. Then we create the vector function. Then what you want to solve is this vector function equals 0, right? So this is the one we want to solve. Then Newton's method finds zeros, right? Newton's method finds zeros. So let's briefly review Newton's method. Newton's method said this one. X output equals X input, right? Minus Fx input, and then f primed of x input, right? This is the Newton's method. I asked you to somehow derive these things on the exam, right? On the exam you derive this. Then you see the advantage of deriving these things. Only difference is this part rewritten. So I break up this thing into this one. Did I handle the different thing or the same thing? The same thing, right? Sorry. Is it better? Then the next step is this one. This is the number version, right? Or one-dimensional version. In one dimension, when you handle numbers, division is possible. But now we are handling vectors. In other words, when you replace these things by vectors or matrices, there is one part that we cannot directly copy. What is that part? Do you recognize the part? Right. In matrix, we cannot handle division, right? In matrix, we cannot handle division. So only this part should be converted to matrix version, and that conversion is F primed inverse, right? But F primed is not even defined, right? Because of this reason, we use something that replaces F in vector calculus. So it is called Jacobian of F function. Jacobian of F function replaces this part. So this is the difference between the previous and the current one. So I will write the vector version. So x vector, x, right, this is a vector. X out vector equals x in vector minus Jacobian of F, right? Jacobian of F that I will explain one more time. Calculated, this vector calculated at x input, right? X input vector. Right? This vector, this inverse calculated at this vector multiplied by capital F of x in vector. So this is the Newton's method in the matrix form. So essentially, we are handling the same thing. The only difference is the reciprocal, right? There is no reciprocal in matrices. So instead of reciprocal, we use inverse. But we don't have